The second part of the video is going to be about the existence and uniqueness of so-called analytic solutions. So let me remind you of what analytic functions are. I'd like to say this is a standard term, elementary functions. Those are functions with a name, such as cosine and sine and trigonometric and logarithmic and root function and those things. So the basic examples of the function you learn in mathematics is called elementary functions. So try to put that in this diagram so that elementary functions are part of this slightly bigger class of function, which is called analytic functions, which I stated there. This is what we want to explain it here. And some of you might think that, oh, that's all, but it's actually not. There are functions out there. It's infinitely many differentiable, but it's still not analytic. So those are functions are there. So the calculus, the main class of functions are these infinitely differentiable functions. And inside it has something called analytic functions. So here's the review of what analytic functions are. Namely, that locally, if a function has locally power series expansion, then it's an analytic function. So remember that not all functions, the infinitely differentiable function, has this power series expansion at every point. So here's an example of a power series. So however we argued, suppose we have argued that there is this function y equals f of x. Abstractly, we prove the existence of the function, and we realize that it actually has a power series. So for example, at C1, if you look at the C1, we can think about function values around the C1 as a power series. So all the function values around C1 can be, no matter how transcendental or complicated this function is, can be expressed as infinite sum of the simple powers, which involves only simple arithmetic. But there's something called the radius of convergence, such that this way of computing this difficult function value in an easy way doesn't hold for all the values, but something that's close to the C1 value. So there is this right-hand limit and left-hand limit, such that this connection valid only for x values in between these two values. So if you can't use this formula at the beta 1, this is alpha and beta, or something to the right of beta 1. So what are we going to do if we want to compute in here using this type of idea? And what you have to do is that you have to figure out different coefficient than ak that works over here, which is written here. For example, beta 1 doesn't make sense. If you plug in the beta 1, this kind of diverges. Then what we can do is that we're going to actually look at this power series expansion at C2. So however you calculate it through the derivatives, and now those are the formulas for the bk. And then it turns out this power series with a different coefficient only valid just around this much, for example. So we can only use this one over here, so it covers something to the right of beta 1. And to take care of this part and that part, you have to come up with a different power series that works for that function. So although we are looking at this single function, you may have to deal with different power series to take care of the values over here and over there. So multiple power series together may define one function. There are many mathematical objects out there. We only have understanding through this glimpse through that, and never have an actual picture of how it looks like. So that's an analytic. When we say this function is analytic, then every time you choose a pointer here, locally, just around the neighborhood of the C1, we have a power series expansion. When we're lucky, sometimes this radius of so-called radius of convergence is big enough, so this works for all the real numbers, such as sine and cosine and exponential. So this is going to be an example of the uniqueness inside the analytic solutions. So we're not showing that the uniqueness of infinitely differentiable solutions just inside the analytic. If there are analytic solutions, there it must be only one kind of functions. So because analytic solutions is described at central base point C, So we have to look at, okay, around the C, there was only one analytic and expansion. So here we are assuming and it exists and checking its actual solution is in the later part. So we can start here with that assume its analytic solution exists. If it exists around C, it must be in that form, and we show that it pretty much completely determines what this AK is. And I'm clarifying the meaning of this expansion, especially it starts at A0, so you don't have to worry about x minus c raised to 0th power in the case when x equals c and 0 raised to 0th power. The meaning of this notation as a function, it starts with A0. The rest of the part, there is no ambiguity. Now, differential equation involves the derivative, so we're going to differentiate one time and one more time and do this arithmetic. So we're going to do the arithmetic of this infinite sum. So it is a theory you might have learned at the end of Calc 2 that if the function is given as an infinite sum like this, differentiating really is done by differentiating this term. So differentiation is an operator, so we're doing this operation to the left and to the outside of the sum here. But it can go inside through this infinite sum, and that's the part of the theory. If you think about it, and that's not that simple because of this infinitude of the sum. So that became a serious part of this theory. So you can actually differentiate inside. So namely, if you have to differentiate of this infinite sum, we can swap the order and do the differentiation and do the infinite sum later. Then it's actually the same. And if you think about it, there are lots of examples. The order of operation makes a difference, and that's exactly what we're doing here. So if you differentiate this, and that's a constant part, k comes down in k minus 1, and you notice that this index changed to 1. Because the first time a is 0 becomes 0, and here, if k is 0, it already picks up the 0 part right here. So it will be still correct if I write k equals 0 there, but if you write it like k equals 1 because k equals 0 doesn't matter, that makes our manipulation a little bit easier later. So here comes the second derivative, so we have to differentiate this one more time. So k minus 1 comes down, and that becomes k minus 2. And we have these three coefficients. Again, I changed the index to k equals 2 because k equals 1 was before, but we have k minus 1, so that part's going to be 0. So k equals 1 there, k equals 2 there, it's going to be the same because it's the sum of these terms. So we got that part right here, double second derivative, so we have to calculate the 4 times y. Y is here, and 4 is constant, so it can be multiplied inside and there. So we have this guy. So we want to add this y double prime and plus 4y, and through this infinite sum expression. So the following technique is going to be very, very useful throughout this differential equation course. Is we're kind of rewriting this thing such that this sum end have the same power. Right now, if you're looking at the kth power, maybe you want to rearrange this one so that this indexing starts with the kth power. So if you have kth power and kth power there, you can simply just add the coefficients. So we're going to keep this one in this form. We're about to reindex this one such that this has a new index L, and this is simply Lth power. So here's reindexing. So we want to call this k minus 2 L, so that it looks like x minus c, just the Lth power, and rewrite everything else in terms of L. So here's the important identity here, or equation. L is going to be k minus 2, and all the k is going to be L plus 2. Is it here? So k minus 2 is replaced with L, and there are these k's, all these things will be replaced by L plus 2. So that's L plus 2. L plus 2 minus 1 is L plus 1. Now think about k equals 2. K starts with a 2. When k equals 2, and L starts with 0, so it should be reindexed with L equals 0. And when k approaches infinity, goes to infinity, of course L goes to infinity as well. So it's kind of relabeled and all the numbers here in terms of L. So I missed that L plus 2, so I wrote it in there. So watch out the following part. This one has here, it says we're going to add up all this thing from 0 to infinity. So what you see down here is exactly the same thing of this one, but it has this different name of index, k going from 0 to infinity, and now all the L's are switched to k. Right. Now, quickest way to make yourself believe these two things are the same thing, therefore y double prime can be written as like this, is that you go and list them down. L equals 0, you write the first term down, and k equals 0, you write the first term down, and make sure that these two things are the same. When L equals 1 and k equals 1, that term is going to be exactly the same, right? So the y double prime is now written in terms of this dummy index L, and you can always change that dummy index k. Then once you write it like this, then if you compare with the full k, which has this index k, then we kind of re-indexed such that the power part has the same letter k. So you can compare this one with that and how it changed. Now if you add these two, it's completely same, exactly the same index range, 0 to infinity, 0 to infinity. And the sum end has this common factor, so we will just add this coefficient. So here's y double prime, and here's a 4y. So if you add them, then you can see the x minus c to the k is here, and index is exactly the same. I collected those coefficients in front of it. So as you can see, I set this one, not set it, this is supposed to be identically equal to 0, because that's our original equation. This double prime plus 4 times this unknown function y is supposed to be the 0 function. If a power series is a 0 function, that means all the coefficient must be 0. So that gives us some relationship between this fictitious coefficient ak. Now this is the coefficient part of the y double prime plus 4y, and we're setting this one equal to 0. So if there is a solution, the coefficient of the power series must obey this law for all the indices, and this is k. So it involves ak and then ak plus 1. So this is usually called the recursive relation. If you can isolate this ak plus 2, and you can calculate that ak plus 2 using this ak value. So if you isolate this one, you can do your algebra. It turns out this is the value for all these k values. So if I know a0 and I know a2, if I know a2, then it's going to be a4, it determines. If I know a4, it determines a6. So if you understood this much, like I said, a0 completely determines all the even indices. If I know what a1 is, it completely determines 1 goes to 3, and 3 goes to 5. It completely determines the values of odd indices. So first we write that values c1 and c2, whatever that is. So those are the very first even index, and that's the very first odd index. So I'm going to use this a0, some value c1 I assigned, to calculate a2. So when k equals 0, that's a0, and a2 is determined by this formula. So k equals 0, that makes this part 2. K equals 0 make that part 1. So that's why you see 2 times 1. And 4 is always there, and negative is part of the formula. So whatever the c1 is, a2 must be that c1 times this number. So since we know a2, we can determine what a4 is. So let's apply the same thing to a4 here. a4 has this 4, and to get this a4, k must be 2. We're applying k equals 2, then you get a4. So k is 2. So k2 goes in there. Negative 4, when k equals 2, that's a 4, and that's 3. So it's a 4 times 3. So that must be this part. And this part must be a2 here. But we know what a2, how a2 looks like, so that will replace that a2 spot. So I replace that a2 within here, and you can rewrite this whole thing with 2 copies of 4, and you might recognize this 1, 2, 3, 4 multiplied. That's a 4 factorial. So there it is. 4 squared, negative, negative disappeared, 4 factorial and C1. So that must be the shape of A4. So again, like I said, A4 is completely determined by the C1. So here's how A6 goes. A6, if you use that recursive relation, K has to be 4. And this time I want you to go back to the formula and do this one yourself. That what's in front of that A4 is this one. So we pick up 6 and 5, and this is a slot for A4, which we found in this one. So I replace it here. So you can see the denominator is 6 factorial and picks up third power of 4, and it picks up negative again. And of course you don't want to do this one forever. You want to kind of get a nice formula by observing what's happening to these numbers involved in here. This is not so complicated example, although you might still find it's complicated. It's relatively less complicated. It's not difficult to see these example A0, A2, A4, A6 and to come up with good candidates of a formula of this one, which is this one here. So if you write it, this one with a 2L, you can write that right hand side in terms of L. What you see down there is exactly 2L factorial, and you're picking up the copy one at a time because we're skipping over these even indices. That's exactly the 4 to the L, and C1 was always there. The sign was alternating, and make sure you get this L or L plus 1 to match the correct sign. So by stating this, you will definitely check all these 6 coefficients and use something called a mathematical induction to actually perfectly prove, and this is the formula. And if you have that recursive relation up there, right, like this. So let's look at odd indices. So odd indices case, it goes exactly the same, except that we start with a different number, C2, and recursive relation here, and takes you all the odd numbers. So I did the calculation here. I want you to pause the video and do this part yourself and see if you can actually formulate the answer like I did here. So I summarize it here. If you have analytic function at C that satisfies this second order differential equation, those coefficients of the power series expansion is completely determined. The even indices look exactly like this, where C1 is some unknown factor involved, and A2L plus 1, and this is completely determined where C2 is another unknown fact. So there's still free part. So if you put down some conditions to this C1 and C2, some condition, it'll completely determine the C1 and C2. So with the determined C1 and C2 value, and this whole coefficients are determined, so that proves uniqueness. So what kind of condition will determine the C1 and C2? Those are turns out the typical initial value condition. So here they are. So here's what C1 and C2 are. C1 was the very first even index, A0, and C2 was A1. So you can actually write those A0 and A1 as values of something like this YC and Y double prime of C. So why is that? Is this the Taylor coefficient formula? So if you write down the power series, that AK, that is the coefficient in front of x minus c to the kth power, and if you have a function, and the relationship between this number and the values of the derivative is the following, that AK is the value of the kth derivative divided by k factorial. So A0 will be the 0th divided by 0th derivative divided by 0 factorial, that's exactly YC. A1 will be the first derivative y prime of c divided by 1 factorial, that's that. So if we are given a condition, the initial value and initial first derivative value, that determines the C1 and C2. Therefore, we are given this C1 and C2, and rest the coefficient is completely determined. Now, if you think about it, that concludes the uniqueness of the solution of the analytic solution, uniqueness of analytic solution of this differential equation with that initial condition. Completely the coefficients are determined. Now what I'm trying to do in this part here, I'm putting those formulas together and then see if you can discover the solution in a slightly different form. So I wrote down, these are the entire power series expansion. So I collected those even indices and odd indices separately, because we have a formula for this one, formula for that one, and it's like given different formulas. So I separated like this. And I substitute the formula we had it before. So it's only showing the odd index formula, for example. So odd index formula showed exactly here, if you compare it. And C2 is missing, but it's supposed to be here. I think it's up this side of the board, but C2 should be there. But I got the C1 since it's showing everything. C1 here, and then that was the formula. And I realized if I substitute this one with a Z and that one with a Z, it's easier to recognize, or it's easier to simplify. And that's what I'm doing down there. Is one part that's tricky, is that this whole thing is called a Z, so that's Z to the 2L, but I put this 4 to the L inside this 2L power. So 2 to the 2L is a 4L. Got a little bit trickier here. This is 2 to the L plus 1 is supposed to be. Sorry about this part not showing. This is L plus 1. Then we have this Z to the 2L plus 1. We have 4 to the L plus 1. So if you have 2 in there, it's going to give you 4 to the L, but it's a plus 1 only gives you 2. So, but we have a full copy of 4 in here, so it's missing a copy of 1, one copy of 2. So since that's a constant, I put it outside. So this one is 2L plus 4th power, and this one is 2L power. Look like that. So everything is shown correctly in this slide, so I pulled it up and shown it here. So I organize it this way so that you might recognize this coefficient that is -1 to L power 2L factorial down there, and -1 L plus 1 with 2L plus 1 factorial down there. So this is exactly the coefficient of the cosine x. This is exactly the coefficient of the sine x, except there's one copy of 1 in there. So I made that mistake down there, but it's supposed to be just L. You can pull that out outside, so it becomes -2C2. So here, this whole thing can be written as a cosine of 2Z. That whole thing is a negative. It's supposed to be negative 2C sine 2Z. So let's substitute back what the Z was. Z was x minus C, and that's what you have, a 2 times x minus C, and it can be pulled up here. So that's the actually closed form. You don't have to use a power series. You can actually write it just like this. That's the exact form of solution to that differential equation shown here. So C1 and C2, like I said, completely is determined by the values at C and values, the derivative value at C, and C is our choice. Okay, what I want to do in this part is rewriting the solution we had there. Right, this is a solution we had, and these came from the power series we discovered. But if you think about it, the radius of the convergence of those power series is infinity. So this C part is not that important, although the C part is used in the initial conditions. But usually the way the solution to that equation is written is not in this form, but it's a different form that does not involve this C value in there, which is namely this one, just the cosine 2x and sine 2x with some coefficient in front of it. So if you actually apply this functions to that differential equation, then they do satisfy. And you can find the C1 prime and C2 prime that satisfy the initial value condition. So I'd like to explain these two parts. Let's first think about the logic. C is given, and maybe we chose C, and the uniqueness argument says that every solution must be in this form. Therefore, if you discover that this function happened to be the solution of the differential equation, because of our uniqueness proof, this must be true. So given C1 and any given C1 prime and C2 prime, anything you write down like this, there must be an appropriate value C1 and C2 such that this will exactly equal that as a function. And the proof of that is uniqueness theorem. This is the solution. It must be in that form. That's the uniqueness part. So I will state that later again, but right now the calculation I'm going to go through is that, okay, that's the most general form. It involves a C. But it happened that this looks nice, and then we want to replace this general form of the solution with this one. So what we have to show is that given anything, the C1 and C2, we choose an arbitrary C1 and C2, and some center position C, and we write down these trigonometric functions. Can this be actually written like this, such that this now it becomes a general form of a general solution, not this one? So look at this one here, arbitrary, given C1 and C2. Here's a general solution, our theory says. But can that be replaced by this form so that we can just use this one as a general solution? So given in C1 and C2, let's find C1 prime and C2 that covers this one. It is just a simple trigonometric identity. So this part's given, C1 and C2, and center base point is given, so we can expand it using addition and subtraction formula of cosine and sine. So I expanded this one using the law of cosine, and this one addition formula of sine. So you can check that. Since we want to compare this one, sorry about that, compare this one with this one here, we wanted to turn this one into this form. I'm going to collect cosine 2x and sine 2x. So here, there's a cosine 2x, and there's a cosine 2x. So if you collect these two terms and factor out, and this is remaining, and there's a sine 2x, and there's a sine 2x. If you collect these two terms and factor out sine 2x, then this is what's left out. So I want you to pause the video and see if this factorization and gathering is done correctly. So if you compare that with the C1 prime and C2 prime, that must be the coefficient C1 prime, that must be the coefficient C2 prime. Right. The question is that, again, given C1 and C2, and base point is given, can there be a C1 and C1 prime and C2 prime that satisfy this condition? That the C1 prime has to be this number, C2 has to be that number. It's that easy. It's done. We found that C1 prime and C2 prime. That makes these two things exactly equal to C1 prime cosine 2x, C2 prime and sine 2x. Let me summarize it again. If I start with this very general form, and there will be C1 prime and C2 prime such that this is expressed in that form. So it is not some special form, but this is actually now a general form. So we can use that. And the advantage is that this form does not have C in it. Let me address the other questions. So what about C1 prime and C2 prime? These are the coefficient in front of cosine 2x and sine 2x. That was part without C. Easy answer, which I gave you at the beginning, was that both the analytic function, by the uniqueness of what we have proved, and the C1 prime, C2 prime is the special form of a function that does satisfy differential equation. Therefore, there must be C1 and C2. This is a general form, C1 and C2. The equation involves C1 and C2 is a general solution. So there must be C1 and C2. It's the abstract proof. So what I'm doing in the second part is I'm going to actually compare those two formulas and actually argue more directly that given C1 prime and C2 prime, there is a C1 and C2. Now if you look at this equation, the question is given C1 prime and C2 prime, so we know this number, but we don't know C1 and C2. But C is given, that's the base point. So I'm showing you that this can be rearranged as a linear equation, and this is usually the matrix form of this linear equation. C is given, so these are the coefficients of C1 and C2. Those are the unknown we're calculating. So it can be written as this matrix form, and these numbers are given. The solvability of this linear differential equation depends on the the value of the determinant of this 2x2 matrix. And I calculated there, it has a 2 in it, so it turns out it's 2 is a common factor. You multiply these two numbers, you get the cosine squared. Multiply these two and change the sign, so that's a sine squared of the same argument. Therefore, this whole thing by the identity becomes 1, so the whole determinant is, no matter what your C is always 2. So that proves this direct proof of the given C1 and C2 prime. We calculated these two values, C1 and C2. Thanks.